Hello. In this video, I'm going to solve a statically determinate torsion problem. Okay, so this first video, we're going to be working with a uniform shaft. It's about the most simple problem type. Okay, so as you can see, it's one shaft of uniform geometry and composition. It's 1 meter long, made of steel, which has a shear modulus of 85 gigapascals, has a diameter of 5 centimeters, and it has two loads applied to it. Halfway across from the left is a 20 newton meter load applied in clockwise, and on the far right is a 100 newton meter load applied in counterclockwise fashion. Okay, so what we can do is we can start entering this into the program. Okay, so your first pop-up here is reminding you that the first thing you do is break it into segments. So how many segments do we have? Well, this shaft is entirely just, as far as geometry and composition is concerned, it's uniform. So what you can do is you can break that into just one big segment. Now, there's also sections which also consider the loads applied. So because of this, there's a segment, or there's a load applied in the very center, which would break it into two sections. So you could either just have the segments you input here just split up the same as the sections for consistency, or you can just say it's one long segment and then that's that. If you break it into more segments, then it's going to want you to put in more geometry information, of which for this one it would be the same for both segments. So for now, let's just put in one segment. Okay, so for segment 1, the length total is 1 meter. The outer diameter, 5 centimeters. Shear modulus, 85 gigapascals, which is 10 to the 9th. There's no inner diameter or inner shear modulus because this is solid. So enter that. Now it wants our polar moment of area, or the moment of inertia, which we can calculate with this equation here. Comes out to a fairly small number. Okay. Now that we've put in the geometry, now it wants us to put in our loads. So how many torques are there? Well, there's 2 of them. This pop-up is a reminder of how power works. If you're given the power and the angular velocity, then you can solve for the torque. However, we're just given torques straight up. So we can just enter that. And make sure that your torque is in the correct units. In this case, we're metric, so it's newton meter. So working from left to right, we've got this 20 newton meter in clockwise. Note here that the convention is that counterclockwise is positive and clockwise is negative. So halfway across, it's negative 20 newton meters. And for the final one, it's on the far end, so at 1 meter, we have 100 newton meters. And that's positive because it's in counterclockwise. Okay, and our clamp, the right end is free, the left end is clamped. Here it's just reminding you the difference between segments and sections. This one's going to have 2 sections because of that load applied in the center. And we can draw it. There it has it drawn for us. Okay, we can begin the solution. So here we're looking at section 2. We're going to work from the right towards the left clamp. So on the end of section 2, we have the 100 newton meter torque. in the opposite direction, we're going to have the reaction torque within the material. Summation of forces, it's going to come out to equal 100 Newton meters. Here we have solving for the maximum shear stress. Remember these equations in the basic ideas video, where we have the torque times the diameter divided by 2 all over that polar moment of area we solved earlier, coming out in pascals. So let's start putting this in. So the torque is 100. The maximum shear stress okay. Here I have solved for the maximum shear strain, but the program doesn't actually ask for it, but this is how you would solve for it and what the value would be. And then for twist, TL over GJ. So 100 times the length, which is half a meter, divided by GJ, which are both given. Remember, twist is in radians. We can check. Okay, looks like those values are all right, and we can move on to section 1. Now section 1, you can see now we have the 20 Newton meter load applied. So when you sum up your moments, it's going to come out to T1 is 80 Newton meters. So maximum shear stress, maximum shear strain, twist, it can all be solved. Now recall, even though I'm showing section 2 on here, we're just worried about section 1. Use the length of only section 1, and we can solve for all these values. So let's put in these values. So the torque outer, 80, or 100 minus 20 is still 80. So, and shear stress, twist, and we can check. Okay, solution complete. The program will automatically sum up the amount of twist to get your net twist in radians. As you can see here, I've also solved for it here. Okay, so that's it. That's all there is to it. Fairly easy. In the next video, I'm going to be solving a problem that has a hollow section in it.